Hey everyone, Sakonia here. Today we're going to be solving this integral, and I'm so sorry for my voice if it sounds really nasally because I've currently contracted the flu, but nonetheless we're here ready to solve another math problem, so sorry for the voice. But we are going to be solving this integration problem. Integration 0 to pi over 2 of x sine x cos x dx over sine to the power of 4x plus cos to the power of 4x. And I've given you two hints if you want to try this problem and give this problem a go on your own, but right now I'm going to go over the solution. So first things first, I'm going to apply the first hint actually, but in order to apply the first hint, I need to know what this a is. And this a is the upper bound. This a is the upper bound, and the upper bound in our problem is pi over 2, so a is pi over 2. And before I actually do any of that, I'm going to set this equal to I because we're going to be solving for I, and it's going to come in pretty handy later on. So I'm going to say I is equal to integration 0 to pi over 2, and now this part, instead of f of a minus x, is going to be f of pi over 2 minus x. So basically, wherever I see a x in the original problem, I'm going to replace it with pi over 2 minus x. So let's do that right now. There we go, we have applied the first hint. Now we can simplify this because I know that sine pi over 2 minus x is equal to cos x, and cos pi over 2 minus x is equal to sin x. Now you might be wondering, why did we even do this? I mean, from the original problem we can clearly see that just the sin x and the cos x changed. In other words, sin x was over here, now we have a cos x. Cos x was over here, now we have a sin x. The reason we did this is because now we're going to apply that neat trick I was telling you guys about with the I. So I'm going to label this as the first equation and this as the second equation, and I'm actually going to add them. And by adding them, I mean that we're going to add the i's and we're going to set them equal to the integrals. So let's actually explain that in action. So I'm going to do I plus I, which is equal to 2i, and integration of 0 to pi over 2, and I'm going to add this, and I'm going to add this together. And once I do, that simplifies to a pretty neat integral, which is, and the reason I could do this so easily is because they already had the same common denominator, so I just needed to add the numerator, and they also had the same bounds, the same lower bound and the same upper bound, so I could add them even more easily. Now, in order to simplify this, I'm going to take the pi over 2 outside the integral. And from here, I'm actually going to apply u substitution, and you'll see why in a second. So I'm actually going to let u equal to sine squared x. And the reason for that is because if I take the derivative of both sides, as we're supposed to do with u substitution, we're left with du is equal to sine x cos x dx. And we can see if we divide both sides by 2, we get 1/2 du is equal to sine x cos x dx, and that is exactly our numerator right over here. So we could just replace this for 1/2 du. So two things to note over here. What I've done, I have substituted the numerator for 1/2 du, I have substituted sine to the power of 4x for u squared, and I have simplified cos to the power of 4x as 1 minus sine squared x squared to simplify it, because I want to get it in terms of sine because that is what our u is in terms of. So I could rewrite this as, note that I haven't set the bounds over here. I left the bounds intentionally, I didn't put them, because we have to change them in terms of u, because 0 and pi over 2 was when the integral was in terms of x, but now our final integral is in terms of u, so we got to compensate for those bounds. So in order to do that, I know that when x is equal to the lower bound, which is 0, u is equal to sine squared of 0, which is just 0. And we're going to do the same thing for the upper bound. When x is equal to pi over 2, then u is equal to sine squared of pi over 2, which is just 1. So our new bounds are going to be 0 and 1. Now I'm going to simplify this a bit further. I'm going to take that 1/2 out. Alright, took that 1/2 out. Now I'm going to divide both sides by 2. Alright, now over here we can apply our second hint. But in order to do that, let's actually start simplifying the denominator first. So the reason I simplified the denominator first is to show you guys that we can't just directly apply this formula. On the left side of this formula, we see that the coefficient attached to x squared is just 1, but in this case, the coefficient attached to u squared is 2. And in this case, x squared and u squared, they're used interchangeably. And in order to do that, let's just take 2 outside of the denominator. Now, once we have done this, our second step is to make a whole squared, because I see that over here we have x squared and we have a squared. So a squared automatically means a constant, but x squared means u minus 3 squared, for example. Like, we have to have a u in there somewhere. But over here, we don't really have a u minus whatever squared. We just have a u squared and a u. So let's actually try to complete the square. Our denominator will be u minus 1/2 squared plus 1 over 2 squared. And this is exactly equal to this, just basic algebra completing the square. Now we are ready to apply our second hint. So our second hint is going to say that we have 1 over a. 1 over a, we know a is equal to 1/2, since 1/2 is the constant. Then we have a tan inverse of x over a. Our x is going to be u minus 1/2, u minus 1/2. And if you're unfamiliar with this, I did make a whole separate video pertaining to formulas like these, so go check that out if you have a little bit of hesitancy with this. But if you don't, then let's carry on. So we have u minus 1/2 over a. A we said was 1/2. And then we don't need this plus c since we're doing definite integrals. So 0 to 1. Let's simplify this. And our final answer, once we have simplified, is equal to pi squared over 16.